Hi, this is Hyunjun Jang, and today I will review Learning to Speed Up Structured Output Prediction, which is published in ICML 2018. Many natural language processing and computer vision programs need predicting structured output such as labeled sequence, tree, or general graphs. Structured output prediction requires solving inference problems by searching for score-maximizing output structures. The search space for inference is typically large and grows with input size. Even for some algorithms, the time complexity required for prediction is equal to n to the power of 5. Current practice in NLP is to treat each new sentence as a fresh, discrete optimization problem and pay the computational price each time. To solve this problem, this paper proposes a scheme that learns to make a trained structured predictor faster without losing output quality. We can view each prediction of trained classifier as an opportunity to learn how to navigate the output space more efficiently, and it could make some decisions without needless computations. Before we explore the main idea of this paper, we should know some background knowledge. The first one is integer linear program, ILP. The main experimental setting is based on ILP. In ILP, all of variables are restricted to be integers, and there are several linear constraints. In this situation, we want to find our objective. For example, in this figure, we want to find the x that minimizes the C transpose x, and there are several linear constraints. This is ILP, and this paper used ILP for convenience analysis of structure. Beam search is an approximate search strategy that tries to solve the problem in an efficient way. In its simplest representation, beam width B is the only tunable hyperparameter for tweaking translation results. B in general decides the number of words to keep in memory at each step to permute the possibilities. As a part of step 1 to beam search, the decoder network outputs the softmax probabilities of the top B probabilities and keep them in memory. Let's say M, going, visiting are the top 3 probable words when the first word is I. As a part of step 2, we hardwire the Y1 in the decoder network and try to predict the next probable word if Y1 is already occurred. Our aim is to maximize the probability of Y1 and Y2 occurring together. Again, to work in step 3, we take top B probable Y1, Y2 pairs from step 2 and hardwire them into the decoder network and try to find the conditional probability of Y3 and repeat these steps. Heuristic is a method that might not always find the best solution, but is guaranteed to find a good solution in reasonable time. And by sacrificing completeness, and it increases efficiency and useful in solving tough problems which could not be solved any other ways, or solution take on infinite time or very long time to compute. The classic example of heuristic search method is hill climbing. Hill climbing measures the closeness of the current state to the goal state. We first evaluate the initial state if it is goal state and quit, otherwise current state is initial state. And select a new operator for this state and generate a new state. Evaluate the new state. If it is closer to goal state, then current state make it current state, and if it is no better, then we will ignore it. Finally, if the current state is goal state or no new operator available, then quit. or otherwise we repeat this procedure. Lagrangian relaxation is a technique well suited for problems where the constraints can be divided into two sets, which are good constraints, with which the problem is solvable very easily, and bad constraints that make it very hard to solve. The main idea is to relax the problem by removing the bad constraints and putting them into the objective function, assigned with weights. For example, we should find the x that satisfies the ZIP is mean C transpose x, and AX is greater or equal than B, DX is greater or equal than D, and X is integer. When the AX is greater or equal than B is bad constraint, it makes the problem intractable. To solve this problem, a dual variable for every constraint of AX greater than B is introduced. The vector lambda is the vector of dual variable, which is Lagrangian multiplier. For a fixed lambda, consider the relaxed problem. By assumption, we can efficiently compute the optimal value for the relaxed problem with a fixed vector lambda. Before we see the main idea of this paper, let's check some notations for it. Input X is the preprocessed sentence, like Blondet's sentence, for example, Colin went back home in Orden village. And Y is produced structure associated with input X. Y can be three types of entities, which are person, location, and organization. And phi xy is the relation between input and output, and it can be the kill, live in, work for, located at, organization based in. This figure shows an example of the entities and relations. The nodes are entity candidates, and the directed edges indicate relations. A standard way to model the prediction problem requires learning a model that scores all structure in YX and searching for the score maximizing structure. For this, we use a weight vector alpha, and using dot product between phi and alpha, we calculate the score of the model. And the goal of prediction is to find the structure Y star that maximizes this score. Learning involves using training data to find the best weight vector alpha. In general, Y is a set of k categorical inference variables y1, y2 until yk, each of which can take a value from a predefined set of n labels. The feature function phi can be decomposed into a sum of features over each yk, each denoted by phi k. Then, the goal of prediction is to find the structure Y star that maximizes this score. And to simplify the cost, we dot product between alpha and phi, and define indicator z to indicate yk is assigned to label li. For example, if y1, Colin's entity is person, the z 1 by 1 is 1 and zi over 1 will be 0. This paper used the pre-trained structured output prediction classifiers as a reference classifier, and it is called Blackbox Classifier. To see the mechanism of Blackbox Classifier's learning, we should know the cost of Blackbox Classifier. Using previously defined notation, we can represent the cost of any structure Y by using summation of score C and indicator Z. So, the Blackbox Classifier learns to minimize the cost of structure. Clearly, each categorical variable can take exactly one label. So, the summation will be 1. In addition, We can define the set of valid structures Y using a collection of M linear constraints. These structural constraints characterize the interactions between the categorical variables. For example, if a directed edge in example is labeled as lived in, and then its source and target must be a person and a location respectively. Bottom equation shows these constraints. Directly applying the black box solver for the large output space may be impractical. An alternative general-purpose strategy for inference involves framing the maximization of score as graph search problem. General graph search problem requires defining an initial search node I and a successor function S and goal test. The successor function S maps a search node to its successors. The goal test determines whether a node is goal node. Usually, each search step is associated with a cost function, and we seek to find a goal node with the least total cost. We will denote a generic search node in the graph as V, which corresponds to a set of partially assigned categorical variables. Specifically, we will define the search node V as a set of pairs K and I, each element of which specifies that the variable yk is assigned the ith label. The initial search node I is the empty set since none of variables has been assigned when the search begins. For a node V, its successor SV is a set of nodes, each containing one more assigned variable than V. A node is goal node if all variables yk have been assigned. Finding a shortest path in such a search space is equivalent to the original ILP problem. Various graph search algorithms can be used for performing inference. For efficiency, we can use beam search with a fixed beam width B. When search begins, the beam B0 contains only the initial node I. We define the function breadth expand, which takes the beam Bt as step t and generates the candidate Ct plus 1 for the next beam. And define the function filter. Filter takes the top B nodes according to some priority function Pv. So far, we saw the general structured output classifiers learning and inference mechanism. In here, we will see an inference algorithm that learns regularities across outputs to become faster at producing structurally valid outputs. Before seeing the algorithmic aspect of such an inference scheme, let us first see a proof of concept for such scheme. Our goal is to incorporate the structural constraint as a heuristic for beam search. To do so, at each step during search, we need to estimate how likely an assignment can lead to a constraint violation. This information can be characterized by using a heuristic function hv, which will be used to evaluate a node v during search. The dual form of ILP in above three equations justify the idea of capturing constraint information using a heuristic function. Let uj represent the dual variable for the jth constraint, and using Lagrangian relaxations, we can get below equations. The dual function zU is minimization of LZU, where the minimization is over the domain of the z variables, and denote U star is argmax of ZU as the solution to the dual problem. And by following the theory of Lagrangian relaxation, previous minimization problem will solve the original ILP, which is minimize the summation of C minus summation of U and A multiplied by Z. In here, we define the path cost GV as the summation of C, and heuristic function h star v as summation of a and u. By adding path cost and heuristic function, we can define the priority function PV that ranking the nodes. Since it is a minimization problem, smaller priority value PV means the higher ranking during search. However, it is computationally expensive that compute for every input instance. This paper approximates the heuristic function as a classifier that learns to prioritize structurally valid output by multiplying W and relation feature phi V. To explain the algorithm to learn speedup classifier, this paper assumed we have access to a trained blackbox ILP solver which can solve the structured prediction problems. To define the algorithm, we need additional terminology. We define a node V to be Y-good if it can possibly lead to the reference solution. We define a beam B is Y-good if it contains at least one Y-good node to represent the notion that search is still viable. We denote the highest length in the beam by V hat, and finally, we define an operator setGood which takes a node that is not Y-good and returns each corresponding Y-good node by fixing the incorrect assignment according to the reference solution. This is the algorithm for learning a speedup classifier using Blackbox Classifier. It begins by initializing the weight W to the 0 vector. We iterate over the example for m epochs, and for each example xi, we first solve inference using the ILP solver to obtain the reference structure y. Next, a breadth expand search is performed. Every time the beam B is updated, we check if the beam contains at least one Y-good node that can possibly lead to a reference solution Y. Search terminates if the beam is not Y-good, or if the highest ranking node we have is a goal. If the beam is not Y-good, we compute the corresponding Y-good node V star from V hat, and perform a perceptron style update to the speedup rates. We then check V hat agrees with the reference solution, and if not, we perform similar rate update. And so far, this paper have shown that a structured prediction problem can be converted to a beam search problem. The priority function for ranking search node is determined by PV equals GV plus HV. Ensuring heuristic function be trained to enforce structural constraint. However, computing the path cost GV involves calculating the corresponding ILP coefficient is time-consuming step. If a search node is strongly preferred by the heuristic function, the path cost is unlikely to reverse the heuristic function's decision. In this case, we can rank the candidate search nodes with heuristic function only. Let's define the heuristic gap large delta T as the difference between heuristic value of node V and its successor, and define the path cost gap small delta T as the max difference between nodes. They assumed if heuristic gap is bigger than the path cost gap, then we using only heuristic function to select the beam BT will have the same set of nodes. And the path cost gap is approximated by empirical parameter theta because it needs computationally expensive. So finally, the priority function is defined as below. For the training of Blackbox Classifier, it is used 1441 sentences and 30,000 sentences are used to train the speedup classifiers. There are three types of entities, which are person and location and organization. And there are 5 types of relations, which are kill, live in, work for, located at, organization based in. And also, there are two constraints. First one is specifying the allowed source and target argument. For example, if the relation label is live-in, the source entity must be a person, and the target entity must be a location. And the second one is, for every pair of entities, they cannot have a relation label in both directions between them, which means one of the directions must be labeled as no relation. This table shows the result of various search algorithms' prediction speed and accuracy. First two rows shows the result of F1 score against the gold labels. The proposed algorithm with beamwidth 2 shows the best result. And as you can see, the prediction time is smaller than previous ILP algorithm and much smaller than current constraint search algorithm. In intermediate two rows shows the score about the ILP prediction. And validity ratio means the ratio about how much the algorithm matched the prediction with ILP. As you can see, the predicted output is quite similar to ILP and much faster. And this paper empirically verified the idea that we do not always need to compute the path cost if the heuristic gap is large. For both beamwidth, theta equals 0 is the case in which the original model is completely ignored. All the nodes are ranked using the speedup heuristic function only. Even though it has perfect validity ratio, the result is rather poor when evaluated on F1 score. When theta increases, the entity and relation F1 scores quickly jump up, essentially getting back the same accuracy as the speedup classifier. But the prediction time is lower compared to previous results. This paper developed a search-based strategy that learns to mimic a black box inference engine, but is substantially faster, and further extended this strategy by identifying cases where the learned search algorithm can avoid expensive input feature extraction to further improve speed without losing accuracy. And this paper also empirically evaluated proposed algorithm on the problem of extracting entities and relations from text. This is the end of my presentation. Thank you for listening.